A first spectroscopic method that is used to study biomolecules is circular dichroism. So, as I said, circular dichroism is a spectroscopic method, and more precisely, it's an absorption spectroscopic method. And in fact, you can use this method to evaluate quickly the percentage of secondary structure of a protein, to follow conformational change, to study the effect of the environment on the structure, study folding, the denaturation process of proteins or DNA, but also to study the dynamics of biomolecules. See, here, circular dichroism needs only small quantities of biomolecules, and finally here the measure is quite fast. So this method is useful if you would like to have global information about your structure in a quite short time. So what is the principle of circular dichroism? In fact, what we will first do is to polarize circularly the light. So what do I mean when I say that I will polarize the light? In fact, you can see an electromagnetic wave as a vibration of or an oscillation of the magnetic field and of an electric field. And so here the plane in which you have this vibration is various. I will represent this by this double arrow, and you have in fact all the possible planes where you have this vibration. When you polarize a light or a beam, in fact, what you will do is to select only one plane. And so after polarization, you have one plane in which the electric and magnetic component of the electromagnetic wave is selected. So that's a classical polarization process. Here, what we do in circular dichroism, in fact, we polarize circularly the light, and that means here that the norm of the electric field vector is constant, and at a fixed point in space it will describe a circle as time progresses. In fact, when you have chiral molecules, and this is the case of proteins, this is the case of DNA and so on, in fact the way the chiral molecule will absorb the right-handed and the left-handed, the right circularly polarized light and the left circularly polarized light will be different. And what we will do here is to measure the difference in absorption between the right and the left circularly polarized light. There is a law that makes a relationship between the absorbance and different quantities. And this law is the Beer-Lambert law. So what is the Beer-Lambert law? In fact, the Beer-Lambert law says that the absorbance of a sample is equal to a constant that is characteristic of the sample, which is called the molar extinction coefficient, times the concentration of the molecule in solution times the length of the optical path. So here you have a cell. In this cell you have a solution with, for instance, proteins in solution. Here you have a light, and what you will measure, it's the absorbance of the different protein molecule here, and how the light will be absorbed by the proteins in solution. And here L is the length of the optical part of the optical path, sorry. And so of course if you increase this length, of course the quantity of light that will be absorbed will be larger. If you increase the concentration, of course the quantity of light that will be absorbed will also increase. And here what you do is to measure the difference of absorbance of the right and left polarized light. Here you see that you have also the molar extinction coefficient, and this molar extinction coefficient is different for the right and the left polarized light. So here what you will measure is the difference in absorbance between the left and the right polarized light. And so what you measure, it's called the molar ellipticity, and the molar ellipticity is proportional to the difference in molar extinction coefficient showed on the previous slides. Here you have a typical graph of the ellipticity in function of the wavelength, and here you have a different spectrum that have been obtained for different types of secondary structure of proteins. And so here you see that the spectrum for helices, here in red, is very different compared to the spectrum obtained for beta sheets or for turn here in orange, and so on. And so you see that according to the spectrum you can deduce the secondary structure content of your protein. You see that we take this spectrum in the range of 190 between 190 and 300 nanometer. So here you see that you are in the ultraviolet part of the spectrum, and keep in mind when I explained the principle of spectroscopic method and of absorption and emission spectroscopy, we have seen that when you have transitions in the UV part of the spectrum, that means that you are following transition between electronic level. Okay, so you see also here it's another example that the spectrum can depend on the experimental conditions. So that's the first remark. And a second remark, of course, when you have, for instance, a protein, in fact, you have a mixture between alpha helices, beta strands, coils, and so on. And so the global spectrum that you will obtain is also a mixture between the spectrum that is characteristic of the helices, the spectrum that is characteristic of the beta strands, and so on. And the weight of the different part in this spectrum is depending on the secondary structure content of your protein. So if you have, for instance, 50% of alpha helices and 50% of beta strand, the global spectrum that you will measure is obtained as a a weighted linear combination of 50% of the spectrum that is characteristic of the helices plus 50% of the spectrum that is characteristic of the beta strands.